welcome back. So in our first video, we've talked about the basic concepts of projectile motion. Now, we will be dealing with the different equations that we will be using in solving projectile problems.
Remember that the horizontal and the vertical component of a projectile are independent to one another. So, it is better to classify the equations that we can use in solving the quantities in the x component and the ones to be used in the y component. Even with the independence of the two components, there is still one thing that makes them connected, and that is time. You see, the time it took for the object to reach this level is just the same time that the object uses for it to cover across the distance here. Note that in horizontal projections like this, the time that you will solve in either of the components will be the same time that you can use in other component. However, you need to be very careful when using the time in angled projections like this, because the time in the x component here will be the doubled value of the time in the y component. Here are the following equations that you will be using to solve projectile problems. If you look closely at the equations, you will notice that we are making use of subscripts. These subscripts will help us to be able to identify which of these equations will be used to solve for the x and the y components. Obviously, x stands for the x component and y stands for the y component. Other subscripts include the f and the I. Say for example, vf and vi. So vf, the subscript f, indicates final velocity, while in vi, the subscript I indicates initial velocity. These formulas are derived formulas from the kinematic equations. Looking into the g, which is the gravitational acceleration, it is replacing a, which stands for the horizontal acceleration in general. To solve for the horizontal velocity, you can use these formulas. First, we have Vx is equal to d over t, where Vx is the velocity, d is the displacement horizontal or the range, and t is the time. Next is Vix is equal to Vi cosine theta. The Vix here indicates the horizontal component of the initial velocity once the object is launched at a certain angle from the horizontal. And the third one is Vx is equal to Vix is equal to Vfx, considering that the horizontal velocity is constant. Therefore, the initial velocity and the final velocities are equal. To solve for the vertical velocity, here are the following formulas. Vfy is equal to Viy plus gt. Viy can be equal to 0, especially if the object starts to move down from a maximum height. Next, Viy is equal to Vfy minus gt. Vfy can also be 0, especially if the object moves up and reaches a maximum height. The third one is Viy equals Vi sine theta. This formula can be used to determine the vertical component of the initial velocity after the object is launched at a certain angle from the horizontal. The fourth one is Vfy equals square root of Viy squared plus 2gd. Here, Viy can still be equal to 0, especially if the object is moving down from a maximum height. And the last one, VIY equals square root of VFY squared minus 2GD. VFY can also be 0 if the object reaches a maximum height after going up. To solve for the horizontal displacement, these are the formulas. dx is equal to Vx times small letter t. We need to emphasize small letter t here because it is equal to the time it took for the projectile to move from the lowest position to the highest position of the trajectory, or it is half of the time taken by the projectile to cover the whole range in a complete parabola. The next formula is dx is equal to Vx times big letter T. Big letter T here stands for the time it took for the projectile to cover the whole range in a complete parabola, which is equivalent to 2 times small letter t. To solve for the vertical displacement or the height or the maximum height, these are the formulas. dy is equal to Vfy squared minus Viy squared over 2g. Here, Vfy can be 0 if we are talking about the projectile at the maximum height moving from the lowest position, or Viy is equal to 0 if we are talking about the projectile moving from the maximum height to the lowest position. Another is dy is equal to Viy times t plus gt squared over 2. Viy can be equal to 0 if the object starts from rest, that is, it's moving from the maximum height down to the lowest position. To solve for the time in the horizontal component, we can simply use the formula t is equal to dx over vx. T can be big or small, depending on the use. Say for example, small letter t is the time taken to cover a certain range in a half parabola, while big letter T is the time taken to cover a certain range in a whole parabola. To solve for the time in the vertical component, these are the formulas. T is equal to square root of 2 dy over g. This formula is a derived formula from d is equal to Viy times t plus gt squared over 2, where Viy is equal to 0, and t is equal to Vfy minus Viy over g. Vfy can be equal to 0 if the object reaches the maximum height upon its ascent, or the Viy can be equal to 0 if the object starts its descent from the maximum height. Time in going up is equal to the time in going down. It is very important for you to solve time in any of these components because it would mean that you will be able to solve any other quantities of any of these components as well. Acceleration in the x component is equal to 0 because the horizontal velocity is constant, while the acceleration in the y component is always constant, which is equal to negative 9.8 meters per second square. Note that before using these equations, you need to write the quantities given in the problem. And by doing that, you also have to remember that velocity, displacement, and acceleration are all vector quantities. So be mindful in putting signs, whether it's positive or negative, before the value of each quantity. For gravitational acceleration, however, use always negative 9.8 meters per second squared, since it is due to the Earth's pull of gravity, which is directed always downward.